This is the finale for 15 lessons you specified, drew, and graded. Now you build a complete emulation end-to-end in real Python on real data. The question, does quitting smoking cause weight gain? The data is NHEFS, a classic public dataset of smokers followed for about a decade. And the whole pipeline you have learned becomes concrete, a causal question posed as a target trial protocol, mapped to data in a 2-column table, fed to an estimator and shipped with a defense. One twist sets the tone. The crude spreadsheet answer says quitters gained 2.5 kilos more than continuers. That number is wrong, but not in the direction a beginner expects. Start with eligibility and time zero. Just honest filtering, 1,500-odd smokers with a measured weight change. Now the naive comparison. Among people who kept smoking, average weight gain, about 2 kilos. Among quitters, about 4.5. Subtract, and the crude difference is 2.54 kilograms. A spreadsheet would report that and stop. But quitters are not a random sample of smokers. They tend to be older, heavier smokers, exactly the people who gain less weight anyway. So this crude number is confounded. Hold on to 2.54 and watch where it goes. The primary estimator, straight from the flowchart's left branch. Inverse probability weighting. Model who quits, given age, sex, how much and how long they smoked, exercise and weight at baseline. Build stabilized weights and check the alarm. Mean weight near 1, max around 4.3. Healthy, no monsters. Then run the marginal model on the pseudo-population, and the effect is 3.44 kilograms. Look at the direction. Weighting moved the estimate up from 2.54 to 3.44. The confounding had been hiding the effect because older, heavier quitters gain less regardless. This is the mirror image of the statin story, where confounding faked a benefit. Here it masked a real one. Confounding has no preferred direction. Now the cross-check lesson 11 promised. The G formula models the outcome instead of the treatment, a completely different set of assumptions, predicts everyone's weight change under quitting and under not, and averages. It lands at 3.46, right next to IPTW's 3.44. Two estimators that fail in different ways agree. Then handle the 63 people missing a 1982 weight. Treat it as censoring. Add inverse probability of censoring weights, and the estimate barely moves, 3.4. Censoring was nearly ignorable here, and that is itself a finding worth reporting. 3 methods, 3 roads, 1 neighborhood. Now the punchline the whole course was building toward. Lesson 13's lab promised you would hand-roll clone-censor-weight. So why didn't we? Because quitting smoking is a point treatment, assignable at baseline. The estimator flowchart sends a point treatment to IPTW, not to clones. Forcing clone-censor-weight onto this question would be Lesson 15's sin in reverse. The heaviest tool for a question that did not ask for it. You reach for clone-censor-weight only when the strategy references time after baseline, a grace period, a duration, a dynamic rule. The estimator is chosen by the design, not by habit. That sentence is the whole of Module 4. And the defense, so it is an estimate and not an anecdote. The 3 estimators already triangulate, report all 3, not the prettiest. Truncate the weights and check it barely moves. Add a negative control outcome, like baseline height, that quitting cannot cause. Run those, and you can write the sentence 16 lessons were for. Quitting smoking causes roughly 3.4 kilograms of weight gain over a decade, stable across 3 estimators, a censoring correction, and a positivity stress test. That is the difference between a number and a defended estimate. You can now specify, emulate, estimate, and defend. The course is complete. Go run one of your own.